Welcome to Fundamentals of Artificial Intelligence. We are discussing planning today, but with a slightly different perspective. So far, planning and the algorithms of planning that we have looked at, we had made certain simplifying assumptions that really do not hold in the practical world. Certain things like incomplete information or incorrect information needs to be handled by a planner for a real world application. On the other hand, a planner can also look at a given plan to be made up of a number of sub-plans, and given a library of plans, in principle, it may be possible for the planner to get these sub-plans and recreate the required plan. In this lecture today, we will particularly look at two algorithms that exploit such construction of plans. One we called the hierarchical task network planning, and in the second we would look at conditional planning. Now, real world planning domains, as I have been emphasizing, are complex and they do not satisfy the simplifying assumptions of strips and the partial order planning that we have been discussing so far. In fact, here I would like to quote a paragraph from the Russell and Norvig book, pages 367-368, wherein it is said that in complex real world projects, it is common to use scheduling tools such as part charts or critical path method. Now, these tools essentially take a hand constructed complete partial order plan and generate an optimal schedule for it. It is because of the very fact that real world domains are complex. For most practical applications, however, there may be related problems to solve, and therefore it is worth to describe the domain and then have the plans automatically generated. Now, it is often necessary that if a plan fails, one can replan quickly to get the project back, and the traditional part charts do not contain the causal links and other information needed to see how to fix a plan, and therefore this idea of practical planning holds tremendous importance. We will today look at practical planning in terms of what is called the hierarchical task network. But in order to look at hierarchical task network planning, it is important to realize what are the drawbacks of strips like formulation, or to be more precise, why is the strips language insufficient? Now, the strips language cannot express a couple of key concepts. The first among them is the very hierarchical plans. For example, I am talking of a plan for launching a spacecraft. Now, this obviously is more complicated than shopping for groceries or getting a book, a cake, and some other stuff from the market. One way to handle this increased complexity would be to actually specify plans at varying levels of detail, and I may have a number of different levels in which I will generate plans, and finally from a very abstract plan I would get to a level where the plan would consist of only executable actions. Now, this ability to represent hierarchical plans is not there in the strips language. But adding this ability to represent hierarchical plans can make the resulting plan not only computable, but really easier to understand. The next key concept that is not possible to be expressed in strips is complex conditions. Now, strip operators, if you remember, are essentially propositional. For example, there is no universal quantification, and without universal quantification, it may not be possible to describe facts that certain operators impact all objects in the domain. Strips operators are actually unconditional. Now, another thing that is not possible to be expressed in strips is time. If you recall, strips is based on situation calculus, and it assumes that all actions occur instantaneously, and that one action follow another and there is no break. Now, this is a very rudimentary model of time. Any real world project would need a better model of time, and this is one very important concept that needs to be looked at if I have to move these strips like planning algorithms for practical planning. Now, the time model that one need to have must represent the fact that projects have deadlines, actions have durations, and steps of plans may have time windows. Another important concept which is not possible in a strips language is representation of resources. Now, resource limitations are there in the real world, and resource limitations may be placed on the number of things that may be used at one time or on the total amount that may be used. In a strips like representation, it is not possible to talk of such resources. Now, whenever I am talking of action descriptions, in a real life scenario, action descriptions must incorporate resource consumption and resource generation, and planning algorithms must be able to handle constraints on resources efficiently. This could be resources as mundane as money for the grocery planner, or it could be very important resource of time itself. Now, if you look at planning vis-a-vis scheduling, then planning, as we have seen up till now, is about having one or more goals and then generating a sequence of actions to achieve the goal. So, traditionally planning is done with specialized logical reasoning methods, whereas scheduling is about having a set of actions and constraints and allocating resources and assigning time frames to the actions so that no constraints are violated. Traditionally, scheduling is done with constraint satisfaction, linear programming, or other operation research methods. However, planning and scheduling are closely interrelated, and in the real world scenario, one needs to realize that it is very difficult to have them in two separate compartments. One needs to look at planning and scheduling together. So, we will talk of a job shop scheduling problem. The problem that a factory solves is to take in raw materials and components and assemble them into finished products. So, for such a factory, the planning task is about deciding what assembly steps are going to be performed, and the scheduling task is about deciding when and where each step will be performed. Now, just for our own interest, it is important to know that companies like Hitachi use a partial order least commitment planning approach for job shop planning and scheduling. And in Hitachi, a typical problem involves a product line of some 350 different products, 35 assembly machines, and over 2000 different operations. Traditional scheduling methods such as PART are capable of finding a feasible ordering of steps subject to time constraints. And this is where a automated scheduling algorithm is required, where it would represent and reason with additional constraints over and above those that are there for. So, we will look at hierarchical decomposition here today. Hierarchical decomposition or hierarchical task network planning is when you look at a given task at an abstract level, and then you can look at that task being made up of subtasks and go on decomposing this until you are able to get down to actions, and then you have a plan involving the actions. So, here you use abstract operators to incrementally decompose a planning problem. For hierarchical decomposition, there are a number of terms that people use. Some authors use the term operator reduction, that is about reducing a high level operator to a set of low level ones, and some use operator expansion, that is look at expanding a macro like operator into the structure that implements it, that is at the level of the actions. An abstract operator in a hierarchical task network planning can be decomposed into a group of steps that forms a plan and that implements the operator. Now, as I was telling you in the very beginning of this lecture, these decompositions then possibly could be stored in a library of plans, and then one could retrieve them as needed to actually construct the complete plan. Primitive operators in such a hierarchical task network actually represent actions that are executable, and as you can make out now, as I keep on decomposing the different operators, I finally reach to the final level of the plan, which are the primitive operators. So, in a sense, the non-primitive operators represent goals, that is abstract actions that require further decomposition, and the plan is complete when every step is a primitive operator, one that can be directly executed by the agent. Now, let us look at what we mean by the hierarchical task network planning for plan to build a house. Now, if I am talking of a plan to build a house, my plan could be as abstract as build house, and the hierarchical decomposition of the operator now, which is the most abstract operator, build house, could be to decompose this into a partial order plan, where I am thinking of obtaining the permit and hiring a builder, thereafter doing construction and finally paying the builder. Now, as you can see, this plan that I am trying to build, the most abstract operator that I could think of was build house, and I could decompose it into construction and obtaining permit, hiring builder and paying the builder. Now, a little thought will let you see that the construction operator could again be decomposed to its sub plans like build a foundation, build a frame, and then I can think of building the roof and the walls, and thereafter building the interior. So, to make the idea of hierarchical planning work, we need to provide an extension to the strips language. Now, this extension needs to allow non-primitive operators, and I should be able to modify the planning algorithm to allow the replacement of non-primitive operators with its decomposition. So, in terms of extending the language, first we would need to partition the set of operators that we have to deal with, and the partition could be into primitive and non-primitive operators. Now, the distinction between primitive and non-primitive operators is actually relative to the agent that will execute the plan. Second, we would need to add a set of decomposition methods. Now, these decomposition methods would be some expression of the form decompose OP, which means that I have a non-primitive operator that unifies with O, and I can decompose it into a plan P. Now, a decomposition method is actually something like a substitution for the original operator in terms of its subroutine, or you can look at it as a macro definition for an operator. So, as such, it is really important to make sure that the decomposition is a correct implementation of the operator. So, the decomposition method that we are talking of has an operator O, and a plan P needs to correctly implement that operator. Now, this decomposition that I have, I end up with having a plan. Now, a plan P will correctly implement an operator O if it is complete and consistent plan for the problem of achieving the effects of O. That means that first, when I am looking for the plan to replace the operator, I should be looking for a plan that achieves the effects of the operator given the preconditions of the operator, and thereafter I should look for if P is consistent. Now, P being consistent means that there is no contradiction in the ordering or variable binding constraints of P, and every effect of O must be asserted by at least one step of P and not denied by some other step or later step of P. Finally, every precondition of the steps in P must be achieved by a step in P or be one of the preconditions of O. Then I say that the plan P is complete and consistent for the operator O. Now, it is possible to replace a non-primitive operator with its decomposition and have everything hooked up properly. All one needs to do is check for possible threads arising from interactions between the newly introduced steps and conditions. Now, there could be interactions among the steps of the decomposition itself, but then one need not worry about these interactions. For if I am talking of replacing a non-primitive operator with a decomposition, we will be actually looking at putting the whole plan together, and therefore, we need not worry about interactions among steps of the decomposition itself. Hierarchical planning allows very complex plans to be built up from simpler subplans, and as I was referring to, it allows plans to be generated and saved in a library of plans so that it can be used and reused later in the planning problem. Now, in terms of modifying the planner, a hierarchical decomposition planner is a hierarchical partial order planning algorithm. So, one needs to look at how to get to that from the partial order planner. Two principal changes are required. First, the algorithm itself must find a way to decompose non-primitive operators, and second, it must take a plan as input rather than just a goal. Now, if you remember, goal can be represented as a start finish plan. So, this is compatible with the partial order planning approach. Allowing more extensive plans as input means that the guidance can be provided, and with these two modifications, a hierarchical decomposition planner could be arrived at from the partial order planner. So, here is the decomposition of a plan step and how you go about making all things fall in its place. So, if you remember, we were talking of having an operator called build house, which is an abstract operator. In order to have that, one needs to own land and have money. So, in order to own land, you need to buy land, and in order to have money, you need to get a loan. And once you have built house, you would have a house where you can move in. Now, the build house is an abstract operator and could be decomposed to a partial order plan, like I could think of obtaining a permit and think of hiring a builder and having construction being done, pay the builder and then move in to the house. But now, if you notice that one of the causal links to the non-primitive step here, this causal link which was coming from get loan to the operator build house, I have attached to the next later state of the decomposition here rather than to the front of the decomposition, as I have done the causal link for obtaining permit to the front of the decomposition. So, that is what I meant when I said that when we are decomposing a abstract operator into its more lower subplans, then the causal links will fall in its own place. And here one of the causal links that lead to the non-primitive build house ends up being attached to the first step of the decomposition, and the other one is actually at a later step. So, this causal link gets attached here and the other causal link gets attached here. The hierarchical decomposition is a good idea on the same grounds that subroutines or macros are good ideas in programming. And it is interesting that the pieces that can be combined hierarchically to create large plans can be done without incurring enormous combinatorial cost of constructing large plans from primitive operators. Now, if I was thinking of only getting to a very large plan in terms of very primitive operators, the idea of using hierarchical decomposition to create large plans from breaking these non-primitives one step at a time can be done more efficiently. Now, the idea is, how does one string abstract operators together? An abstract solution to the planning problem is what would contain the abstract operators. Now, once we have looked at an abstract operation, finding an abstract solution, if one exists, should not be too expensive. Finding an abstract solution and then rejecting other abstract plans as inconsistent, the following properties hold. If P is an abstract solution, then there is a primitive solution of which P is an abstraction. So, if this property holds, then once an abstract solution is found, we can prune away all other abstract plans from the search tree. This property is the downward solution property. If an abstract plan is inconsistent, then there is no primitive solution of which it is an abstraction. Now, if this property holds, then we can prune away descendants of any inconsistent abstract plan, and this is called the upward solution property. So, here is the downward solution property. In here, each box that I have shown represents an entire plan, and each arc represents a decomposition step in which an abstract operator is expanded. At the top, we have the abstract plan, and at the bottom are plans with only primitive steps. Now, the boxes that I have with bold outlines are possibly abstract solutions, and dotted outlines are inconsistent. So, the plans which are marked with an X need not be examined by a planning algorithm anymore. Now, we can see that here we have the downward solution property, where we see that given a abstract solution, and we can prune away all other abstract plans from the search tree, and in the upward solution property we can prune away all descendants of an inconsistent plan. So, here we could prune away all of this. To get a more qualitative feel for how these properties affect the search, we need a simplified model of the search space. So, here I show a portion of the search space for hierarchical decomposition with depth d equal to 3, branching factor of 3 decompositions per step, and 4 steps per decomposition method. Then a solution will have s to the power d steps, and in our case n is 64. Now, if it is a non-hierarchical planner, then I have to generate these n step plan, choosing among b possibilities for each one of them, and then this would take some time, order of b to the power n in the worst case. Whereas, if it is a hierarchical planner, then the search decomposition would lead to abstract solutions. We can think of exactly one of every b decomposition is a solution, and therefore, the total number of plans to be considered would be summation of some b s to the power d. Now, the planner has to look at, if you see, SB steps at depth 1, at depth 2 it looks at SB steps for each, that is, it is S square B square. However, it only has to decompose 1B of them, so the total is B S square, and therefore, the total number of plans considered is of the order of B S to the power D. Now, for the parameters given here, if I was talking of a non-hierarchical planner, the non-hierarchical planner would have to inspect some 3 into 10 to the power 30 plans, whereas a hierarchical planner would look at only 576 plans. And this is what is a tremendous saving for hierarchical task network planning. Now, few other possibilities in terms of STRIP's language representation itself is about increasing the operator expressivity. Hierarchical planning addresses the problem of efficiency, whereas expressive operator descriptions would make our representation language more expressive in order to broaden its applicability. And we can have 3 types of extensions. 1, allowing for the effects of an action to depend on the circumstances in which it is executed. 2, allowing disjunctive and negated preconditions, and 3 allowing universally quantified preconditions and effects. Now, conditional effects is about operators which have different effects depending on what the world is like when they are executed. For example, conceptually if we are talking of the blocks world, then it has only one action. It is about moving a block from one place to another, and we introduce more operators in the blocks world in order to maintain the clear predicate properly. For example, I have two operators here, one move b x comma y, that is move b from x onto y, and here it is about moving b from on top of x to the table. Here when I say on bx, I mean that b is on x and there is nothing in top of b and there is nothing in top of y. So, I could move b to y, and when I move b to y, I no longer have y clear. Whereas, when I move b to the table, I do not need to worry about the table being clear or not. Now, suppose that the initial situation includes a on b and the goal is to have clear b. Then I achieve the goal by moving a off b. Now, somehow I am forced to choose whether we want to move a to the table or to somewhere else, and this you should be able to realize introduces a premature commitment and can lead to inefficiency. On the other hand, if I combine these two operators somehow using a conditional effects, that is, I still talk of moving b from x onto y and add somewhere here that I do not need to have the fact that d is no longer clear to be in the delete list when y is not the table, then I can see that the effects refer to the situation that the result of the operator and the condition refers to the situation before the operator is applied. So, I can eliminate premature commitment. How did I eliminate the premature commitment? I eliminated the premature commitment by bringing in the conditional effects. So, instead of just adding that once I move b onto y, y becomes not clear and I should have it in delete list, but then I said that y still remains clear if I only need to have it in the delete list if y is not the table, and therefore, I need to have it in the delete list that says that y is no longer clear. And then I have negated and disjunctive goals. So far we have insisted that all goals preconditions be positive literals. Now, dealing with negative or negated literals as goals does not add much complexity. I just check for effects that match the goal. So, treat the initial states spatially, do not want to specify all conditions that are false. So, I should have goal of the form not p either by an explicit effect that unifies with not p or by the initial state if it does not contain p. So, we have disjunctive preconditions. It is easy to add disjunctive preconditions. A step with precondition of the form p or q will lead to non-deterministically choose to return either p or q and reserve the other as a black track point. Now, any operator that has precondition p or q could be replaced with two operators, one with p as a precondition and one with q. but that the planner would have to commit to one. So, disjunctive precondition allows us to delay making the commitment. Similarly, we could have disjunctive effects, and now disjunctive effects are a case like if I have an operator called flip coin, then I would have either heads or tails, and I should be able to express that effects as a disjunction. Now, it is difficult to incorporate disjunctive effects. A disjunctive effect is used to model random effects or effects that are not determined by the preconditions. Now, change the environment from deterministic to non-deterministic, and therefore, it is very difficult to incorporate disjunctive effects. I would also be able to introduce numeric values that can be used as measures. Now, these variables represent resource quantities and change over the course of the plan. Certain actions may produce resources and therefore increase the quantity. Other actions may consume resources and therefore decrease the quantity of the resource. More generally, we may want different type of resources that our planner should be able to handle, like continuous versus discrete, shareable versus non-shareable, reusable versus consumable versus self-replenishing. Now, time can also be any other resource. Two ways in which time differs from other resources is that when I execute actions in parallel, then the maximum of the respective times is what I need to consider rather than the sum, and the constraints on the time resource have to be consistent with the ordering constraint. That is, if I have S1 before S2, then time at S1 must be less than time at S2. Time never goes backward, so no operator generates time instead of consuming it, and that is what we need to take care when we are talking of time constraints. Now, planning and acting in the real world, we have assumptions for flawless planning and execution given the algorithms that we have discussed so far. And these assumptions are that the world is accessible, static and deterministic, similar to that for our simple search methods. In real world, agents have to deal with both incomplete and incorrect information. So, incompleteness arises because the world is inaccessible. For example, in the shopping world, the agent may not know where the milk is kept in a supermarket unless it asks, and incorrectness arises because the world does not necessarily match the agent's model of it. So, the way forward under such scenarios is that we can have two different ways to deal with this problem. One called conditional planning. This is also known as contingency planning, in where we construct a conditional plan that accounts for each possible situation or contingency that could arise. The agent finds out which part of the plan to execute by including some sensing actions in its plan to test for the appropriate conditions. For example, the shopping agent might want to include a sensing action in its shopping plan to check the price of some object in case it is too expensive. And there is another way which is called execution monitoring. In execution monitoring, you have a simple planning agent and now it uses its percepts to select action. Earlier in a simple planning agent, with a plan to execute, there was no possibility of using percepts to select action. So, that was a very fragile strategy. Monitoring what is happening while it executes the plan is what the execution monitoring means. It can then replan to find a way to achieve its goal from the new situation. And for example, the agent discovers that it does not have enough money to pay for all the items it has picked up. It can return some and replace them with a cheaper version. This is called execution monitoring and replan. Now, let us look at one example to finish our discussion today about replacing a flat tire. Now, this example is from Russell and Norvig, Artificial Intelligence, a Modern Approach, chapter 13, pages 393 to 398. Here, the problem is to fix a flat tire. So, at the start, the spare tire is not flat. I have an intake spare, and my tire 1 that I have is flat. I want to go and have a situation where the tire is no longer flat. Now, I have operations that I can remove the tire, or I can put it on the hub again, or I can inflate the tire. Now, any of the standard planners would be able to come up with the following plan. It would talk of removing the tire and putting on the spare. But under incorrect information, that the current state is incorrect. Example, we know that the spare is not intake, or we have incomplete information, that is unknown preconditions, such as that is the spare intake or not, or even incorrect information like missing incorrect post conditions in operators. How do we go about planning? So, the solution for planning in such scenarios is to go for conditional planning. That is, you plan to obtain information from certain observation actions, and then you subplan for each contingency. And like you could look for saying, I would love to check tire 1. If tire 1 is intake, I will inflate. So, this is a conditional plan. Now, it is expensive because it plans for many unlikely cases. On the other hand, you could think of monitoring or replanning, where you assume normal states, outcomes, and you check progress during execution and replan if required. This will lead to failure if I come across unanticipated outcomes. Now, let us look at our first solution of replacing a flat tire, that is conditional planning. So, the flat tire plan begins with the usual start and finish steps. Notice that the finish step has a context true here, which indicates that no assumption has been made so far. And now we have two open conditions to be resolved, on and inflated. And the first is satisfied by adding a link from the start step with the unifier X for tire 1. The second is satisfied by adding the step inflate tire 1, which has preconditions that the tire is flat. But interesting is that it also says that the tire is intake. Now, the open condition flat is satisfied by adding a link from the start step. For the intact tire 1 condition, I need to add the check tire 1 step, which is a conditional link shown as a dotted arrow here, and this is called a conditional step because it will become a branch point in the final plan, and the inflate step and the finish step now acquire a context, which is this plan will work only under the context that the tire 1 is intact, and they are assuming the outcome to be intact tire 1 rather than not intact tire 1. Now, check tire has no preconditions in our simple formulation, so the plan is complete, but this plan is complete given the context of the finish step. Obviously, we cannot stop here. We need a plan that works in both cases, if tire 1 is intact or if there is a hole in tire 1 and you cannot inflate it any longer. So, the conditional plan ensures this by adding a copy of the original finish step, but now labeled with a context which is opposite of the original context. So, it labels it as not intact tire 1. And one needs to remember, if this new branch that has come, if the solution of this new branch requires further context assumptions, then I will keep on adding a copy of the finished step. But for this problem, the only context being intact tire 1 and not intact tire 1, this is good enough. So, now we continue this plan. This very fact that tire 1 has a hole in it, still I can plan, and only way to satisfy the inflated x condition now is by looking at the start, by having spare being replaced for the x, and with this unifier I can add an inflate step for the spare. Now, the spare is inflated, so you satisfy the inflated x condition either by looking at a substitution of x for spare or add an inflate step for the spare. Now, spare is inflated, so you choose the former, and you have now only to add the two conditions, that you remove the tire and put on the spare. The steps remove tire and put on the spare are now added to the plan to satisfy the condition on spare. However, when I am doing this, one needs to realize that the remove tire 1 actually threatens a causal link which is on tire 1 in the finished step, and this I need to take care of. I resolve the threat by conditioning that step so that its context becomes incompatible. So, conditioning is achieved here by finding a conditional step that has possible outcome that would make the threatening steps context incompatible. So, we check and see that this step, which is about check tire 1, can have a possible outcome which is not intact tire 1. So, we make a conditional link from the check intact tire step to the remove tire step, and then this remove tire step is no longer a threat, because it has now got this not intact tire 1 as its context, and the new context is inherited by the put on spare, and the plan is now complete. Now, this algorithm that we have just now looked at is called the conditional partial order planner, and is a good example of conditional planning. There is another solution to replacing a flat tire, as we have been discussing earlier. It is about monitoring. So, execution monitoring, failure would mean that the precondition of the remaining plan are not met, and when the preconditions are causal links at the current time. And action monitoring would mean failure means the preconditions of the next action are not met or the action itself fails. So, both cases one needs to replan. Now, in replan we can go by a very simple algorithm that on every failure you replan from scratch, or better, on failure you plan to get back on track by reconnecting to the best continuation, and you generate a loop until down behavior. Now, to finally conclude our lecture on practical planning and action, we have seen that planners based on extended strips like language and partial order least commitment algorithms are capable of handling complex domains. These domains are as complex as spacecraft missions and manufacturing, and hierarchical decomposition allows non-primitive operations to be included in plans with a known decomposition into more primitive steps. Standard planning algorithms assume complete and correct information. Many domains violate this assumption. A more comprehensive approach is one that we have looked at called conditional planning, and it could involve incremental modification to the plan, including execution of steps as conditions in the environment evolve, which is made possible through sensing and monitoring. Now, these were about planning actions. In our next lecture, we will look at sequential decision problems, where we need to plan not for a single action, but for a sequence of actions. Thank you.